The story begins not with a flash in the sky, but with a whisper in the data. A faint trace of light, barely stronger than the hum of the cosmic background, flickered across a sequence of telescope readings. At first, it seemed like noise, one of those countless transient signatures that tease astronomers night after night. But then, within the gentle curve of plotted brightness, a consistent pattern emerged. It wasn't noise, it was motion. And behind that motion lay something new, something ancient, something that had traveled longer and farther than we can yet imagine. This is the story of comet C 2025 V1 Boris, a new wanderer revealed from the depths of our solar system, a discovery that bridges science and wonder, made by a familiar name in the world of celestial exploration. Gennady Borisov, the same observer whose telescopes once unveiled the second known interstellar visitor to ever grace our skies. Now once again, his instruments have found something extraordinary, an object that might at first glance seem ordinary, but upon closer inspection opens a door to questions that reach to the heart of our understanding of where we come from, and what else might be waiting in the vast dark between the stars. Discovered only a few days ago, Comet Boris, designated officially as C 2020 V1 Boris, appeared quietly against the backdrop of the constellation Perseus. At first there was no spectacle, no glowing tail, no streaming plume, no sudden rise in brightness. It hovered around magnitude 13, faint enough that only medium-sized telescopes could pick it out of the night. Yet beneath that apparent stillness, the numbers told a deeper story. The comet's orbit, published by the Minor Planet Center, showed an eccentricity just shy of 1. That single value, seemingly just another figure in a spreadsheet, tells us everything. It means this object is bound to the sun. It is part of our family, not a visitor from another star, but a returning child from the frozen edges of our own. It would have been easy to overlook such a detail. Yet in astronomy, as in all science, it is the small numbers that reveal the greatest truths. Had the eccentricity been even a little above 1, the object would have been labeled interstellar, another Oumuamua, another messenger from beyond. But as it stands, Comet Boris seems to belong to the long-period clan, a type of comet thought to have originated in the distant Oort cloud, that mysterious spherical reservoir of icy bodies orbiting at the edge of the sun's gravity, tens of thousands of times farther than Earth. From that ancient vault, some small disturbance, a passing star, a shifting resonance of gravity, must have nudged this icy traveler from its deep sleep, setting it on a long, stretched path inward. For eons it drifted through darkness, unlit and unseen. Only now, as it approaches the inner solar system, does sunlight begin to wake it, coaxing vapor from frozen ice, building a coma, a faint shell of gas and dust that begins to glow, like breath in the cold. But there is something strange about Boris. As of now, astronomers have seen only that compact coma. There is no bright sweeping tail, no dramatic outburst. The comet glows softly, steadily, like a lantern behind fog. And in this quiet light, scientists recognize something familiar. The eerie behavior of another object, one that has puzzled the astronomical community for months, Comet 3 Arch-Atlas. That comet, too, showed powerful internal activity near the sun, yet no visible tail. It withstood flares and radiation storms that should have shattered it, and yet remained intact, brightening oddly, and in some wavelengths, even changing color. And now, Boris seems to echo that mystery. Could there be a connection between them? Two comets moving through vastly different parts of the solar system, one inbound, one outbound, both showing anomalies that challenge our models of cometary behavior. Is it mere coincidence? Or is there some hidden mechanism at play, some clue buried in their composition, their spin, their internal chemistry? We do not yet know, but astronomers around the world are watching closely. Right now, Comet Boris lies between Earth and 3i Atlas, about 70 million kilometers from us, a distance so immense it's almost incomprehensible, and yet, cosmically speaking, still close. Its orbit will soon carry it below the ecliptic plane, the flat disk in which most planets move, before it rises again, sweeping toward the Sun for a close encounter on November 16th, at just under half an astronomical unit. That is closer than the orbit of Venus. What will happen then? Will it flare into sudden brilliance as the solar heat ignites its surface ices? Or will it remain quietly glowing, an enigma of subdued light like Atlas before it? Each night, observers report it brightening, though only slightly. Each image brings whispers of detail, a hint of structure in the coma, a suggestion of faint gas jets. Nothing definitive yet. But in science, it is precisely at this threshold, when we do not yet know, that the air feels charged with discovery. Somewhere between certainty and imagination lies the frontier of knowledge. And right now, Comet C 2025 V1 Boris is sailing straight through that frontier, pulling us with it into questions that may reshape how we think about the solar system's own frozen memory. It is tempting to romanticize this, to think of it as a messenger from the Oort cloud, carrying whispers of the ancient nebula from which the sun and planets were born. But perhaps that isn't so far from the truth. Each long-period comet is a time capsule, a piece of untouched primordial matter preserved since the dawn of our system 4.5 billion years ago. When one of them returns, it brings us a glimpse of what the solar system once was, before Earth's continents formed, before life took hold, before even the planets found their stable orbits. And so, in the quiet of the observing stations, scientists prepare. The telescopes align. Spectrographs hum. Data streams begin to form across the networks that connect observatories from Chile to Japan. They are watching for every flicker, every fluctuation, every spectral fingerprint of water, carbon monoxide or ammonia, because in those numbers lies the story of creation itself. What we are seeing now is not just another comet. It is an opportunity to look back through time, through layers of cosmic history frozen in ice. But Boris is not alone out there. Just beyond, still glowing faintly after its solar ordeal, 3I Atlas continues to confound observers. It has changed subtly, but unmistakably. Its orbit is no longer perfectly accounted for by gravity alone. Something has nudged it, something small but real, a non-gravitational acceleration whose source remains uncertain, and that perhaps is where our story deepens. Because if 3I Atlas has indeed been pushed by something beyond the ordinary, and Boris begins to show signs of similar behavior as it approaches the Sun, then the line between interstellar and local, between ordinary and extraordinary, may blur in ways we did not expect. For now, we stand at the edge of that mystery, watching the two comets glide through the black, their paths crossing in the geometry of fate. What secrets do they carry in their frozen cores? What unseen forces move them across the dark sea of space? We will soon find out. Next. As the first wave of data streamed in, the initial uncertainty surrounding Comet C 2025 V1 Boris began to fade, replaced by a growing sense of awe and curiosity. Astronomers across the world were now locked in observation, their instruments trained upon a point of light that represented a messenger from the deep reaches of the solar system. Within hours of confirmation, observatories in Chile, Spain, and Hawaii began feeding measurements to the Minor Planet Center, which in turn refined its orbital model. The results revealed a long-period trajectory, perhaps stretching back millions of years, a cosmic ellipse that carried this object far beyond the orbit of Neptune and then back again, now returning for what could be the first time since the dawn of human civilization. The comet's discoverer, Gennady Borisov, had been scanning the skies with his custom-built telescope from the Margo Observatory in Crimea. For Borisov, this was not a moment of luck, but of persistence. He had spent decades searching the dim frontiers of the sky, chasing objects that flickered in the edge of perception, It was through that same devotion that he had found 2Pi Borisov, the second confirmed interstellar visitor ever observed, whose hyperbolic orbit and chemical composition stunned the astronomical community in 2019. This new discovery, though bound to the Sun, carried echoes of that earlier triumph. Both objects seemed to share a quiet nature, a subdued activity that concealed the complex stories written in their icy bodies. When the preliminary orbit of C-2025 V1 was released, it immediately drew comparison to other comets of distant origin. Its eccentricity, measured just below unity, indicated a solar system native, yet its velocity, inclination, and orbital tilt suggested a trajectory sculpted in the farthest reservoirs of the Oort cloud. That distant sphere, a vast halo of icy nuclei extending almost a light year from the Sun, is believed to be the birthplace of most long-period comets. Each one that falls inward is a relic from the time the planets formed, composed of the same raw material that built Jupiter and Saturn, preserved in cosmic deep freeze for billions of years. Yet this object's story is not only one of origin, but of contrast. As it moves inward, Boris passes beneath the ecliptic plane, diving through the inner solar system before curving upward again toward the Sun. Its closest approach, or perihelion, will occur on November 16th at just under half an astronomical unit, closer than the orbit of Venus. The comet's path places it between Earth and the position of 3I Atlas, the enigmatic object discovered earlier this year, whose behavior continues to defy easy explanation. The juxtaposition of these two travelers, one outbound, one inbound, has given scientists an unexpected chance to study the full spectrum of cometary dynamics under very different physical conditions. In recent weeks, 3I Atlas has become something of a cosmic enigma. As it approached perihelion on October 29th, the comet was bombarded by a series of solar flares and coronal mass ejections from the far side of the Sun. The solar environment it encountered was among the most active in recent years, a storm of radiation that would have torn most fragile nuclei apart. And yet, 3I Atlas survived. Not only that, but it brightened dramatically, increasing its luminosity far beyond model predictions, while displaying no visible dust tail. To an untrained eye, it appeared almost sterile, a glowing sphere with no plume, as if resisting the very physics that govern cometary behavior. To understand what was happening, a team led by David Farninoia at NASA's Jet Propulsion Laboratory recalculated the comet's orbital parameters. What they found forced them to add new terms to the model, A1 and A2, the standard coefficients used to describe non-gravitational acceleration. These coefficients quantify the small but measurable forces acting on a comet due to jets of gas escaping from its surface or other non-gravitational influences. When these values differ from zero, it means that something besides gravity is pushing the object. In most cases, such deviations arise from sublimation, ice turning directly into vapor under solar heating, creating jets that act like tiny thrusters. But the peculiar strength and timing of the acceleration observed in 3I Atlas raised deeper questions. Farninoia's fit suggested that the object was experiencing a continuous, gentle push directed away from the Sun, with a secondary component along its orbital plane. The measured acceleration was small, on the order of a few hundredths of a millimeter per second squared. But over time, such forces can subtly alter a comet's trajectory. For most comets, this process is entirely normal, but the scale of the effect in 3I Atlas, combined with the absence of any detectable plume or tail, made it stand out. If significant outgassing was occurring, it should have been visible, but the instruments detected none. The next step came from Harvard astrophysicist Avi Loeb, who analyzed the energy balance implied by the measured acceleration. Loeb calculated that if the force originated from standard outgassing, then, by conservation of momentum, the comet would need to eject an enormous amount of mass over the coming months, enough to produce a bright, easily visible cloud of gas and dust. If that cloud failed to appear, then the mechanism driving the acceleration must be different, perhaps involving unusual surface chemistry, uneven sublimation, or thermal lag deep within the nucleus. Meanwhile, observational data from the Stereo-A spacecraft and the GEO-19 observatory confirmed an unexpected phenomenon. The comet's brightness increased with proximity to the Sun nearly 7 times faster than normal, and its color spectrum shifted subtly toward blue. This was the first time such behavior had been recorded in a large comet without a visible dust tail. The blue tint hinted at emissions from ionized gases such as carbon monoxide or cyanogen, substances that glow under ultraviolet radiation but do not scatter light the way silicate dust does. It was as if the comet's internal furnace burned with invisible fuel. The European Space Agency's JUICE spacecraft, though primarily on a mission to Jupiter's moons, found itself in a favorable geometric position to observe the object. Its instruments, designed to study gas and plasma interactions, are expected to record data in early November that could confirm the presence of specific volatile compounds in 3I Atlas's coma. If confirmed, the findings might reveal a new class of low-dust, gas-dominated comets, bodies that interact with the Sun in ways previously unseen. For Comet Boris, these developments are more than academic. The similarities between the two objects, subdued activity, compact coma, and possible deviations from purely gravitational motion, suggest a shared mechanism at work, perhaps one rooted in their distant, icy origins. Researchers at the European Southern Observatory and the Subaru telescope are now preparing a coordinated campaign to track Boris through its perihelion passage. Infrared spectroscopy will be key. By measuring the specific wavelengths of light emitted or absorbed by molecules in the comet's coma, scientists can infer its chemical composition, identifying whether it is rich in carbon monoxide, methane, ammonia, or water ice. If the ratio of these substances matches that of 3I Atlas, it might indicate that both comets were formed in similar regions of the early solar nebula. Alternatively, if Boris shows a more typical composition, then the differences in activity could stem from variations in crust structure or rotation rate. These are not minor distinctions. They touch on fundamental questions of planetary formation. The behavior of such comets helps scientists reconstruct how the solar system evolved, how volatiles were distributed, and how much material was delivered to the inner planets during the era of heavy bombardment billions of years ago. Back on Earth, anticipation grows. As Boris draws closer to the Sun, each day offers a new frame in the unfolding drama. Sensitive instruments at the Lowell Observatory, the Atacama Large Millimeter Array, and the Canada-France-Hawaii Telescope have all detected a gradual increase in brightness, though still no clear tail. A few observers report hints of a narrow jet emanating from the nucleus, possibly an early sign of awakening activity. If true, it could mark the beginning of more visible changes as sunlight penetrates deeper into the comet's crust. In many ways, comets like Boris and Atlas are natural laboratories for studying the boundary between the known and the unknown. They test the limits of our understanding of thermal physics, sublimation dynamics, and the subtle interactions between dust, gas, and solar radiation. A comet is not a static object, but a living system, reacting to heat, rotation, and internal stress. Tiny fractures open and close as ices expand and contract. Gas vents escape through cracks, carrying fine dust grains that form the coma and tail. The geometry of those emissions determines how the nucleus moves, sometimes predictably, sometimes not. The mystery deepens further when comparing the trajectories of both comets. Although their paths differ dramatically, the timing of their activity, each showing anomalies near perihelion, suggests a possible connection to solar conditions. The Sun's magnetic field, shaped by solar wind and flares, may induce electrostatic effects on ionized gases, subtly influencing their outflow patterns. In the case of 3I Atlas, such interactions could have produced the measured accelerations without requiring massive outgassing. If similar deviations appear in Boris after November 16th, the theory will gain strong support. NASA's Deep Space Network is already preparing to transmit tracking signals for high-precision orbit determination during Boris's perihelion passage. At the same time, the James Webb Space Telescope and Hubble will allocate brief observation windows in December, once the comet emerges from the Sun's glare. The goal is to measure its reflectance spectrum and thermal emission, essential clues to its surface properties and albedo. If Boris exhibits the same enigmatic brightness increase without dust ejection, it would imply that we are witnessing an entirely new category of cometary behavior, one perhaps linked to chemical or physical processes not yet modeled. But not all eyes are fixed on instruments alone. There is a deeper fascination here, one that transcends numbers and equations. Every comet is a time traveler, an emissary from epochs when the solar system was a swirling disk of gas and rock. To watch one awaken is to see the memory of that epoch unfold in real time. The gases that vent from its surface are the same compounds that once seeded the primordial atmospheres of young planets. The water vapor escaping from its ice may be chemically identical to the water that fills our oceans. The next few weeks will be decisive. As the Sun's energy intensifies, Boris will cross the threshold where its surface begins to vaporize in earnest. Its coma will thicken, spectral lines will sharpen, and with each observation, the scientific community will inch closer to answering one of the most profound questions in planetary science. How much of what we are, our oceans, our air, perhaps even our first organic molecules, was delivered by such wanderers from the cold? Meanwhile, 3I Atlas continues its outward journey, carrying with it the lingering riddle of non-gravitational acceleration. Even now, as it recedes beyond the orbit of Mars, the faint traces of its path remain a subject of study. Every parameter refined, every brightness curve adjusted, feeds into models that will later be applied to Boris. The interplay between these two objects, separated by space but linked by mystery, offers a rare synchronicity in the story of cometary science. And so, the narrative unfolds. A tale of two travelers, one departing, one arriving, each revealing new chapters in the cosmic dialogue between sun and ice. Soon, their destinies will diverge again, one back into the dark, one into the glare of the sun. Yet for a brief moment in time, our instruments, our curiosity, and our shared human wonder are aligned with them, tracing their delicate arcs through the vast, silent theater of space. The answers lie ahead, carried in vapor and light, waiting to be read in the language of spectra and motion. And as we turn our gaze upward, what we are truly seeing is not just a comet, but a reflection of our own desire to understand the forces that shaped us, the same forces that still breathe through the frozen hearts of these celestial wanderers. In the grand mosaic of exploration, there are always the human hands and hearts behind every point of light catalogued in the dark. Among them stands Gennady Borisov, a man whose quiet persistence has redrawn the boundaries of what private astronomy can achieve. Long before the world knew his name, he spent cold nights in a small observatory dome, meticulously assembling his own telescopes from salvaged parts, refining optics by hand, and coding tracking software line by line. There was no vast institutional backing, no array of high-tech instruments, only an unyielding fascination with the unknown and the discipline to pursue it. When he first discovered 2I Borisov, the interstellar comet that bore his name, he not only became part of astronomical history, but also symbolized the idea that exploration is not confined to government agencies or space telescopes. It can begin in a backyard, under an ordinary sky with a single determined observer. Now, With the discovery of C 2025 V1 Boris, his legacy extends into yet another chapter. The instrument that captured this faint traveler was the same one he modified after years of trial. Its mirror reshaped to minimize optical aberrations, its mount upgraded to achieve arc-second precision. In the weeks following the detection, Borisov remained characteristically modest, saying simply that he was fortunate to be looking in the right place at the right time. But those who know the discipline of astrophotography understand that fortune favors the patient. Each comet he has revealed tells not only of cosmic wanderers, but of the perseverance that drives human curiosity itself. And what of the objects he has brought into focus? Their stories span across epochs and unimaginable distances. Comet Boris, now tracing its inward path, represents the ancient material of our own solar system. Its icy crust contains compounds that predate the sun's full ignition, molecules forged in interstellar clouds and preserved in vacuum for billions of years. Studying it gives scientists a direct glimpse into the chemistry that existed when planets were still gathering from dust. In contrast, 3I Atlas, the interstellar enigma, carries the heritage of a different star, born perhaps in a region of the galaxy where metallicity and radiation were entirely unlike our own. Together, these two bodies embody the dual nature of cosmic discovery, one looking inward, reminding us of where we came from, the other looking outward, pointing to what lies beyond. The instruments now trained upon them are among the most advanced humanity has ever built. The James Webb Space Telescope, operating far from the distortions of Earth's atmosphere, prepares to capture the infrared spectrum of Comet Boris after its perihelion. These data will reveal not only the temperature and composition of its nucleus, but also the faint signatures of organics, carbon-based molecules that form the building blocks of life. The European Space Agency's JUICE mission, orbiting in the outer solar system, will soon relay complementary readings from its ultraviolet spectrometer, offering a second vantage point to decode the gases escaping from 3I Atlas's coma. The coordination between ground and space observatories reflects a global collaboration that transcends distance and language. From amateur astronomers feeding nightly brightness reports to professional teams adjusting their instruments in real time to follow new developments. As these missions gather information, the deeper question emerges: what do these comets mean for our understanding of how life began? For decades, researchers have theorized that early Earth was too hot for volatile compounds to remain stable, and that much of our planet's water and organic molecules were delivered by cometary bombardment billions of years ago. Every spectral signature detected in Boris's coma, every molecule of carbon monoxide or ammonia identified, helps refine that theory. If its chemical ratios match those of ancient meteorites, it would support the hypothesis that comets acted as cosmic couriers of life's essential ingredients. If, however, it differs significantly, showing depleted water content or unusual isotopic ratios, it might indicate that not all comets shared that role, and that the story of our origins was more selective and complex than once believed. Comet 3I Atlas, on the other hand, reminds scientists of the unpredictable nature of discovery itself. Its mysterious accelerations, its strange color, and its resilience against solar fury have revived long-standing debates about what truly drives cometary motion. Are these forces purely the product of gas jets, or could they involve electrostatic interactions, magnetic coupling, or even internal processes we do not yet understand? Each anomaly forces astronomers to test the limits of current models, to revisit old assumptions, and to seek new physics where the data demand it. And in that pursuit lies the quiet poetry of science. Every refinement to an orbit, every recalculated parameter is an act of listening to the silent mechanics of nature as it reveals its rhythm in equations and trajectories. When we map the motion of a comet, we are tracing the subtle pull between light and matter, between heat and ice, between the persistence of gravity and the evanescence of vapor. it is a reminder that even in the immense, indifferent expanse of space, there exists order, harmony, and the delicate balance that sustains both planets and the smallest specks of frozen dust. As Comet Boris nears its closest approach, observers prepare for the possibility of transformation. If the nucleus is fragile, it may fragment under solar stress, scattering a cloud of debris that will stretch across the sky. If it endures, it may emerge brighter, with a full, luminous tail, visible in late December. In either case,